So, we talked about a single particle on which a force acts and the particle moves in certain path, and we defined a quantity f dot dl. So, if the particle is here at a certain time and then it moves to a nearby point which we call dl vector, this is the displacement in this small time, and during this the force acting on the particle is some f. So, you can ask what is f dot dl, and essentially this is called work done by the force during this displacement, f dot dl. If the force acting on the particle is f and the displacement of the particle is dl, small displacement, infinitesimal displacement, so that we do not have to worry about variation of this f during this displacement and change in direction of the particle during this displacements. We do not have to worry about those things. This quantity is also called work done by the force during this displacement. Now, the important point was that if I take a finite displacement, if I take a finite time in which this particle goes from here to say somewhere here, and this is b, and I can ask what is the total value of sum of this f dot dl on this path, on this path, on this path, on this path, on this path. I mean, I go along with the particle, I take each small infinitesimal part here, calculate this f dot dl and do it for the entire path from A to B, and then sum all these things. This we call integration. But we will not write A here and B here from A to B, because this particular path is also important. I can also go along some other path and still reach here, and I can ask what is f dot dl here, 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 and so on. An entire path you do this f dot dl and reach L, and these may or may not be equal. So, we say that it is on path 1, certain path is to be specified on which path I have to calculate all these things. So, this is path 1, let us say this is path 1, this is path 2. There may be infinite such paths connecting A and B. Now, there are two possible situations. One is same for all paths, connecting A and B, the end points must be same. We start at A and we finally stop our this integration or this addition at B. So, if it is same for all paths, such forces are called conservative forces. Force is conservative. And remember, even if there is no particle going on the path, but I know that if a particle is here, this will be the force on it. If a particle is here, this will be the force on it. If the particle is here, the force will be this. If the particle is here, the force is this. Even then I can calculate this quantity f dot dl. dl need not be the actual displacement of the particle. I can just draw a path and then construct, okay, here this is the dl, this is dl, here this is dl. I can construct all these dl's along the path, and I know that if the particle is here, this will be the force. If the particle is here, this will be the force. I can calculate this f dot dl. So, whether the force is conservative or not, for that I need not have the physical particle. The force by itself, I can say that it is conservative or it is non-conservative, and if it is not, then it is non-conservative, right. If it is not same for all paths, remember all, It may be same for 10 different paths. It may be same for 10 different paths, but for 11th path, if it is different, then this condition will apply, this condition will not. So, this is called non-conservative. We say that force is non-conservative. Okay. Now, if the force is conservative, and then you take a closed loop, that means I start from a point A and go round somewhere on some path and reach once again A. That means A and B are the same. You start at A, do this f dot dl here, do this f dot dl here, do this f dot dl here and here and here and here and here and here and here. Stop adding here. It is a closed loop. What we can do? We can take some point B somewhere on this path, and then this f dot dl, this let us call it path 1 and this is path 2. So, this f dot dl on path 1, and now the path is, path 1 means you are going from A and stopping at B, and path 2 means you start at A and stop at B. So, connecting the same points A and B. So, this should be equal to f dot dl on path 2, conservative force. We assume that we are talking of a conservative force. In that case, these two paths are same. Now, if I invert the arrows of this path 2 everywhere, what will happen? Each f dot dl will become negative of itself, right? Because here what is the force? That is fixed, that you do not have any control on that. If the particle is here, this will be the force, but dl, it is up to you. You can take this as dl or you can take this as dl. So, if you invert all these arrows here and make it like this, what will happen? What will happen? Now, it is the other side, is the other way. This is f dot dl, and let me call it path 3. Remember, now path 3 starts at B and ends at A, because these are the kind of dl we are taking. So, this is path 3, which is different, starts at B and then it goes this way, this way, this way, this way, this way, and reaches here. And path 2 is starts from here on that same geometrical line, it goes this way, 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 and reaches here. Every dl becomes minus dl, and therefore, these two are negative of each other. Now, bring this thing here. So, you have f dot dl on path 1 plus f dot dl on path 3 equal to 0. And what is this? Path 1 and then path 3, and you are adding. Path 1 means you are going from A to B along this line and reaching here, and then path 3 means you are going from B to A along this line and reaching here. So, you are going on a closed loop. You start at A and you again reach at A after going through this closed loop. So, this whole thing is f dot dl on a closed loop, and for that we put a circle here to tell that it is a closed loop, and this is 0, valid for all closed loops. So, this can be taken as another identifying equation whether the force is conservative or not. If this f dot dl integration, line integration, is 0 on all possible closed loops, the force is conservative. And if there is some closed loop on which it is not 0, then it is non-conservative. and this is also equivalent to, this equation is also equivalent to, some mathematics is needed. What do we say? Point by point curl of the force is equal to 0. The symbol is read as curl of F. What is that? What is that curl of? Essentially, if I am using Cartesian coordinates, your F is a function of x, y, z, and that means Fx is a function of x, y, z, Fy is a function of x, y, z, and Fz is a function of x, y, z. And now you construct this quantity. It is determinant. I am writing I cap here, j cap here, k cap here, then del x here, del y here, and del z here, and fx here, and fy here, and fz here. You know determinant, how to open up a determinant. So, you write this element here I cap, and then in algebra this multiplied by this minus this multiplied by this. Here it will be del y of fz minus del z of fy. So, you will write del fz del y and minus del z of fy, and then similarly you do for j cap part and you do for k cap part. Just as in algebra, you open up this determinant and write the expression. What is this? Fz. Fz is a function of x, y, z. Now, differentiate with respect to y and treat any x and z coming in this expression as constant during this differentiation. This is called partial differentiation, partial derivative. Similarly, here fy is a function of x, y, z and differentiate with respect to z. So, in this expression, differentiate with respect to z and treat any x and y coming in the expression as constant. Similarly, you will have two partial derivatives here and two partial derivatives here. This quantity is called a vector quantity. Remember, so you have I cap here, j cap here, k cap here. So, this is a vector quantity, and that vector quantity is called curl of f. So, if all these are 0, this is 0, this is 0, this is 0, then your force will be conservative. If curl of f is 0, the force is conservative. In this definition, how many closed paths you will check? It may be 0 on 10 different closed paths, but then on 11th it may not be 0. How many closed paths you can check, or how many different paths between the same 2 points you can check? But here it is very foolproof. If you know the force, expression of force in terms of x, y, z, do this operation, and if that turns out to be 0, there is no path and closed or open or this point and that point. If for every x, y, z this is 0, and the expression itself will tell whether it is 0 or not, the force is conservative or non-conservative, you can decide from here. So, this is another way of telling that a force is conservative. For a conservative force, curl of f is 0 at all points. For a conservative force, this integral f dot dl on a closed path is 0 for all paths, all closed paths, or between the same 2 points this integration is same for all paths. So, these are the ways in which you can identify whether the force is conservative or not. Why do we say that the force is conservative? If something of this kind happens, why is the name what is conserved, why it is called conservative? So, that is on the next board. Now, if the force is conservative, I take the first definition, you have 2 points A and B, and you say that this integration f dot dl on this path is independent of the path and only depends on the endpoints A and B. If this is the case, it is always possible to define a scalar function. Remember, this is a scalar, this is a dot product, and then you are adding. So, it is always possible to define a scalar function which we will call V x y z. So, for each point I have defined a particular V. At different points you can have different values of this V. So, you can, it is always possible. So, it is always possible to define a scalar function V such that, right, such that this integration f dot dl, now that it is independent of path, I can write A here and B here. I have to go from A to B, whatever path. So, I can write A and B, A to B, f dot dl, whatever path you want to choose, you can choose, it does not matter. So, this quantity is equal to V at B and minus V at A, and for some reasons I write it with a minus sign. Okay, so, once you ensure me that this f dot dl integration between two given points A and B is independent of path, I can always come up with certain functional form of a scalar function V x y z, so that this integration will be equal to the value of this V at this point B and value of this B at this point A. It is always possible to do that. Okay. And then if this is the case, so this is V A and minus V B. Now, let me do a separate algebra and come out with a different result. What is that? Now, I am bringing a particle of mass m. I am bringing a particle of mass m on which this force is acting, and this is the only force acting on the particle. Okay, so, this is the resultant force. So, F is the resultant force on a particle of mass m, let us say. What is this f dot dr? F dot dl. What is this f dot dl? This f dot dl you can write as mass times dv dt, mass times acceleration, because this is the resultant force. So, I can use Newton's second law. F is equal to m times a, m dv dt and then dot dl, and this dt can go here, and this you can write as m dv and then dot dl dt, and dl dt is v. Okay. In time dt, if the displacement is dl, then the velocity at that point is just this v, and this is half d, or let me write half also inside, d of half m speed square v square. How do I write that? Go in the reverse way. What is half mv square? Half mv square, this is a scalar quantity here, this is also scalar quantity, but in terms of two vector quantities, v vector and dv vector. So, how do I come to this speed square here from this vector thing? So, this you can write as half m v dot v, and then you differentiate d of this, this will be half m and then d of this. How do I do d of this? Product of two functions, keep one function and differentiate the other one. So, v dot dv, then keep the second function fixed and differentiate the first one. So, this is dv and then dot v. Okay, so, just that differentiation of products of two functions, keep one, differentiate other, then keep the second one and differentiate the first one. So, I am keeping this and differentiating this, here I am keeping that and differentiating this. So, this is this. So, it is 2 times v dv dot v, and that 2 cancels with here, and you have m and v dot dv or dv dot v. So, that is here, m dv dot v is equal to d of half mv square. Now, integrate f dot dl, on that path a to b, this is equal to integration d of half mv square a to b, and integration of dx is just x, integration of d theta is just theta. So, integration of this will be just half mv square. So, it is half mv square, and then you put the limits, the lower limit here, the upper limit here. So, it is half m v square at b and minus half m v square at a, and that is kinetic energy at b and minus kinetic energy at a. So, if you have a particle on which this conservative force F is acting, then this F dot dl integration from A to B is equal to change in kinetic energy at B and minus kinetic energy of at A. But the same integration, I said that I can find a, certainly I can find a function V which satisfies this equation. So, F dot dl integration A to B is V A minus V B. If the force is conservative, I can do that. This depends only on A and B, not on the path. This depends only on A and B, not on the path. So, since the same integration is written in two fashions, one is here, other is here, they should be equal. So, V A minus V B should be equal to K B minus K A. V A minus V B should be equal to K B and minus K A, and that means V A plus K A is equal to V B and plus K B. Now, this we name as potential energy of the particle when it is at A, and this is potential energy of the particle when it is B. This V function at x, y, z is named as potential energy of the particle when it is at that x comma y comma z. And this potential energy plus kinetic energy is called mechanical energy. And if I denote it by some other symbol u, which is once again function of x, y, z, which may be a function of x, y, z, then you have this u at A is equal to u at B. So, you go from here to here, your kinetic energy is changing. But if you term this as a potential energy and add to that, the total mechanical energy does not depend on x, y, z, it is same at this point and at that point. So, this is known as conservation of energy. In mechanics, this is known as conservation, principle of conservation of energy. And that is why the name conservative force. Only conservative forces will allow you to define a potential energy, and only then the total mechanical energy will be constant. Now, let me take some examples and then some more questions and discussions on that. Let us take an example of spring force. You have all studied simple harmonic motion, and if you have a particle connected to a spring and one end of the spring is fixed and the equilibrium position where the spring is relaxed, we take that x equal to 0 and then we pull it, release, and it oscillates, and we say that the force is minus k times x, which you also write as minus m omega square times x, and omega is written for square root of k by m. I am not going into great details because you have all studied this motion, very important and very interesting also, but let us go to the energy. Do I have something like Vx? The entire motion is on x axis. So, do we have some function like this? Yes, we do have. It is half kx square or half m omega square x square. This is a function, and the energy of this particle with this kind of force is kinetic energy, which is half mv square and then plus half m omega square x square. And if the particle is at its extreme position, you know, the particle oscillates. If this is the kind of system, and then you pull it and then release it from here, it oscillates, and at extreme points the velocity is 0. That is why it is extreme, and therefore at extreme point at say x is equal to capital A, which is the amplitude, this E is equal to velocity is 0. So, this part is 0 and you have half m omega square and capital A square, x is capital A. And if you write it here, equal to half m omega square A square, you can write what is V. So, this half goes, half goes, half goes, m goes, and m goes. So, you can write what is this V square. This V square is equal to this omega square is here, omega square is here, and then you have A square and minus x square. So, take square root dx dt is equal to omega square root A square minus x square, and now it is very simple, dx by this, dx divided by square root A square minus x square is equal to dx divided by this is equal to omega dt, and you can integrate it very easily, right? You can integrate it very easily. What is that? This is sine inverse of x by A is equal to omega t plus some integration constant, and that tells you x is equal to capital A sine omega t plus epsilon. So, this conservation of energy principle is a quite useful principle. You can see how easily I can get that displacement as a function of time, speed as a function of time, everything, v as a function of x, all those things we get from here. If you start from here and write this as m times d2x dt square, we have to do a greater algebra to reach this point. So, there are many other applications of this conservation principle and the concept of potential energy. So, we will talk more about the concept of potential energy in the next lecture.